G'day. If you're someone who works with outdoor lighting in either Australia or New Zealand, then you absolutely need to get your head around AS/NZS 4282. You can think of it as the official rulebook for controlling light pollution. So in this explainer, we're going to break down the essential workflow for you, from zoning and limits right through to the practical design choices, so you can get it right every single time. At the end of the day, this whole standard really boils down to one thing: controlling what's called spill light. It's pretty much what it sounds like: any light that spills or trespasses beyond the property it's actually meant to be lighting up. And getting this right, well, it's a real balancing act, and the standard gives us the framework to do it properly. So, to get a handle on all this, we're going to follow a really simple workflow. First, we'll dig a bit deeper into the problem itself. Then, we'll move on to what is maybe the most crucial first step: identifying your environmental zone. From there, we'll get into the key technical limits, how to actually apply them in the real world, and finally, how to choose the right gear for the job. Right then, let's jump into why this standard is so important. And look, it's about so much more than just keeping the neighbors happy. It's really about responsible design in our shared environment. What's really interesting is that the standard flat out acknowledges that obtrusive light can be pretty subjective. It's not just a number you can read off a light meter. It's about the real-world effects on people, both physiological and psychological. We're talking about everything from glare that messes with your sleep to just the simple annoyance of having light trespass where it's not wanted or needed. And who is this for? Well, basically everyone involved in the process. We're talking local governments, building owners who are setting the rules, right through to the designers who are speccing the job, and the installers who are on the ground putting it all together. Everyone has a role to play in getting this right. Okay, this next step is absolutely foundational to the entire process. Seriously, before you can do any calculations or choose any lights, you first have to classify the project's location into one of several environmental zones. And this table right here is the key. It classifies every single location into an environmental zone. It ranges from A0, which is for intrinsically dark areas, think national parks or observatories, all the way up to A4 for high brightness areas, like a buzzing city center. The zone you're in dictates all the rules that come next. And the contrast between the zones is pretty stark. In a zone A0, the #1 priority is preserving natural darkness. But in a zone A4, you're working in an environment that's already flooded with light. So as you'd expect, the amount of allowable light spill in these two zones is just worlds apart. And that's exactly why getting the zone identification right from the start is so critical. All right, now we get to the numbers. The standard sets out very specific, measurable limits to control obtrusive light. We're going to break down the two most important ones for you. So first up is vertical illuminance, or EVE. This is all about measuring the amount of light that's falling on a vertical surface, like your neighbor's window, for example. It's measured in lux. Now, just to give you some context, a brightly lit office is around 500 lux, whereas a full moon on a clear night is less than 1 lux. This is really the main metric we use for limiting light trespass. And here's how it's all applied. This table shows the maximum EV that's allowed. You'll notice two key things here. First, the numbers get bigger as you move from the dark zone A0 to the bright zone A4. And second, for every zone, there's a much stricter curfew limit for later at night. So for instance, in a typical suburban A3 zone, you might be allowed 10 lux before the curfew, but that drops right down to just 2 lux after. The second key metric is luminous intensity. Now, this one doesn't measure the light landing on a surface. Instead, it measures the brightness of the light source itself when you look at it from a specific direction. A great way to think of it is like the focused beam of a torch. Its main job is to control glare. And just like with vertical luminance, the acceptable luminous intensity changes depending on the zone. In a dark, rural area, say a zone A1, the limit is 2,500 candela. But you jump over to a bright commercial area, zone A4, and that limit shoots up to 25,000 candela. The logic is exactly the same. The darker the environment, the stricter the controls. So, we've got the rules, we understand the numbers, but where exactly do we apply them? This is where the theory hits the real world, and it is all about the boundary line. The where is so important. Light spill isn't measured on the building itself, but on a vertical plane right at the property boundary. And these calculations, they start at 1.5 meters from the ground and then go upwards. This basically simulates the perspective of a person standing on the next door property. And the location of that calculation plane can actually change. For a standard residential neighbor, like you see here in Figure A, the plane is right on the boundary. But for an environmentally sensitive area, like in Figure F, you might need to apply a buffer zone. That means the limits have to be met even further away from the sensitive area itself. Let's finish up with the most practical part of all this. How do you actually design a system that complies? Well, it often just comes down to a few simple principles for choosing and aiming your lights correctly. Okay, the first principle of compliance is luminaire selection. It's pretty simple, really. Those unshielded globe-style lights that just scatter light in all directions, especially upwards, they are a massive cause of obtrusive light. The solution is always to use fixtures that direct light downwards, exactly where it's needed and nowhere else. And going beyond just directing light down, effective shielding is absolutely key. A simple shield or a cowl or even just a recessed bulb design can physically block light from escaping at high angles. It makes a huge difference in controlling both glare and light spill. Aiming is just as important as shielding, As this diagram shows, even a really good fixture can create terrible glare if it's aimed too high. A key technique here is to keep the main beam aimed below horizontal, ideally below 70 degrees, and make sure the bulb itself isn't directly visible from a distance. This example really ties all those principles together. For lights that are mounted up high, combining good shielding with a narrower beam angle is a really powerful strategy. You focus the light only where you need it, and that dramatically reduces the chance of it spilling across the property line. So, to recap, here is your 4-step workflow. It's that simple. First, you identify the environmental zone. Second, you look up the correct technical limits for that zone. Third, you do your calculations at the property boundary. And finally, number 4, you select, shield, and aim your lights to meet those limits. It's a really logical process that leads to responsible and effective lighting. And that is a breakdown of the core principles in ASN/NZS 4282. It gives us a really solid framework for balancing our need for light with our responsibility to protect the night environment. I think the key takeaway is this: good lighting design isn't just about what you illuminate, but it's also about what you consciously choose not to. So, how will these standards shape your next project?